Hello and welcome to today's video. So in today's lesson we are going to learn about the SPDF electronic configuration. So this is under the quantum atomic theory. So just to give a bit of a background, so we have 4 quantum numbers. The first one is known as the principal quantum number, which is denoted by letter N. So this focuses on the energy level that an electron occupies, and then it's a positive integer ranging from 1 to 2 to 3 and so on. Then we have the second quantum number, which is known as the azimuthal or the angular quantum number, denoted by small letter L. This describes the shape or the sub-levels that are in an atom. It is given by L less or equal to n minus 1, where n represents the principal quantum number. So here, when L is equal to 0, this represents an S. When L is equal to 1, represents a P. When L is equal to 2, represents D. When L is equal to 3, represents F, and so on and so forth. Then the third quantum number is known as the magnetic quantum number, which is denoted by M sub L. This focuses on the orientation of those atomic orbitals in space. Then it's given by negative L less or equal to ML less or equal to positive L. Then the last quantum number is the spin quantum number, denoted by M sub S. So this focuses on the spin direction of an electron, which means the up spin and the down spin. The up spin represented by positive half, and the down spin represented by negative half. Now, as of today, I want us to look at how to write the electronic configuration using the SPDF atomic orbitals. Now, before we go there is need for us to understand the subshells or sub-energy levels and the orbital electron capacity. So what this entails is that we need to understand the subshell, the L value, the orbitals or the number of orbitals, and then the maximum number of electrons that can be occupied by each respective orbital. So we have the S, we have the P, we have the D, we have the F. For now, we'll end on F. So the subshell, when the subshell is S, our L value is 0. When the subshell is P, our L value is 1. When it's D, our L value is 2. When it's F, our L value is 3. Then in terms of orbitals, we only have one S orbital. For the p orbital, we have 3 orbitals. For the d orbital, we have 5 orbitals. Then for the f orbital, we have 7 orbitals. Then in terms of the maximum number of electrons that they can occupy, the s orbital can occupy the maximum of 2. The p orbital can occupy the maximum of 6. The d orbital can occupy the maximum of 10. And the f orbital can occupy the maximum of 14. Now, let's understand what we call the order of filling. So how do we fill the electrons, or how do we choose which orbital to fill the electrons first before we go into another orbital? So this is guided by what we call the Aufbau principle. We'll give more details about the Aufbau principle as we proceed. Now, here what we need to understand is that electrons occupy orbitals in order of increasing energy, not just by n. So what this simply means is that we feel the lower energy level first. So the lower energy level should be filled first. Now, this is determined by, these two rules, which we call the N plus L rule. So when we're using the N plus L rule, we say lower N plus L is filled first. So when we calculate the N plus L, the one with the lower N plus L should be filled first. Then, if N plus L is the same, in a case where the orbitals share the same N plus L, then the smaller principal quantum number fills first. Let's look at examples. What do they mean? So, which one do we fill first when we have 3s versus 3p? So using the N plus L, where we know that N is the energy level, then L is given by N minus 1. So in this case, then we know that L, when L is 0, it means it's S. When L is 1, it means it's P. When L is 2, it means it's D. When L is 3, it means it's F. So if we have a 3s, it means that our N, so for a 3s, our N is equal to 3. Then our S, according to here, our S is 0. So this means N plus L is 3 plus 0. That will give us a 3. Then when we look at a 3p, our N is 3, then our S, according to this, is 1. Our L is 1. Here our L is 0. So N plus L is going to be 3 plus 1, which will give us a 4. So we'll compare these two, and in this case we'll notice that SL and 3S ought to be filled first because it's on a lower side, it's a lower energy level according to this calculation. We can look at another example. B, what of where we are comparing 3P versus 4S. So for 3P, our N is 3, then our L is 1. So meaning N plus L will give us 4. Then 4S, our N is 4, our L is 0. So N plus L will give us 4. So in a case where they are equal, this rule emphasizes that the one with a smaller n should be filled first. So in this case, 3p will be filled first. So we're going to allocate the electrons to 3p before we go to 4s. Let's look at another last example, which is C. 4s are competing with 3d. So 4s, our n is equal to 4, our l is 0. Therefore n plus l will give us 4. Then for 3d, our n is equal to 3, then our l, when we go back to the key here, our L is 2 because it's D. Our L is 2. Therefore, N plus L will give us a 5. So in this case, 4S is filled first. So that is how we choose which particular orbital is filled first. I want us to look at what is known as the filling sequence. So on the filling sequence, we're going to follow what we call the diagonal rule. So for the diagonal rule, we have energy levels this side, energy levels increasing, then we'll have the atomic orbitals down this side. So when we have 1, we have 2, we have 3, we have 4, we have 5, we have 6, we have 7. So those are the energy levels. So in the S, we have the S. In 2, we have S and P. In 3, we have S, P, D. 4, we have S, P, D, F. We'll end on F. 5, we say S, P, D, F. 6, S, P, D, F. 7, S, P, D, F. So using the diagonal rule, let me use this yellow so we can do this. and then it goes like that. So we're going to use this to come up with a standard way of writing the electronic configuration. So this means that we're going to use this standard electronic configuration system, which starts with 1s followed by 2s followed by 2p, then 3s, 3p. So before I go to 3d, there is a 4s, then I come back to a 3d, then I go to 4p, then I go to 5s, I come back to 4d, then 4d, I'm here, then I go to 5p, then I go to 6s, then I come back to 4f, then I go to 5d, then I go to 6p, then I go to 7s, I come back to 5f, then I go to 6d, then I go to 7p. So we can end here for now. So we're going to use this configuration. We'll use this standard system to write our electronic configurations. Now, before we go there, we also need to understand that there are rules that govern the electron arrangement. So we just don't arrange electrons anyhow. There are rules that govern this, and the first rule is known as the Pauli exclusion principle. So what does this rule state? So this rule states that no two electrons in an atom have the same 4 quantum numbers. So no two electrons will have the same 4 quantum numbers. It's either one is spinning in the upward direction, upspin direction, or downspin direction. Then the second rule is called Hund's rule. So Hund's rule of maximum multiplicity states that when feeling degenerate, so degenerate are orbitals of the same energy level. Degenerate orbitals, for example, the p orbital, electrons feel singly. So we feel the electron singly first with a parallel spin before pairing. So what this simply means is, if we're feeling electrons in these orbitals, let's say this is a px, the py, the pz, so we'll put the electrons singly before we can pair. So we put them singly before we can pair. That's what the Hund's rule states. Then the last principle is called the Aufbau. The Aufbau principle. So for the Aufbau principle, this one states that fill from lowest to highest energy orbitals as per sequence above. So the sequence that we have here, so as this particular sequence. So what this simply means is that as the energy is going up, it clearly shows you that the orbitals are not in the same energy level. So the sequence is that 1s is on the lower side compared to 2s, which is on the lower side compared to 2p, which is on the lower side compared to 3s, which is on the lower side compared to 3p, 4s, and then it goes on and on. So we follow this standard. Now let's look at examples. So in this example, we are required to write the electronic configuration using the SPD format. So for example, we're given hydrogen. Hydrogen only contains one electron, so there's only one electron there, which only means that we are dealing with 1s and 1. If we are looking at carbon, so carbon is 12, 6, so there are 6 electrons. So following the standard is 1s with 2, then 2s with 2, then 2p with 2. So that is a configuration for sodium. Let's look at calcium. Calcium is Ca20. So 1s2, you remain with 18, 2s2 remain with 16, 2p6. So we have 10, we're remaining with 10. So it'll be 3s2, 3p6, and 4s2. So that is the electronic configuration. So if you're trying this for the first time, your job is just to know this format, and then you'll just be replacing by filling in the number of electrons, where you have to know that the maximum number of electrons in this case is given by this. For each respective orbital that you're dealing with, that is the maximum number of electrons. So let me give another example. This is D. So A, B, C, D. Let's look at sodium. Sodium is Na with 11 electrons. So it's going to be 1s2, 2s2, 2p6, then 3. This is 11, 3s, 3s. So we have 1, 2, 3, 4, 3s, 1. So when we add these electrons, they should be giving us 11. Okay, this one is done. Let's look at DE. So we have what we call a condensed formula. I'll just give one example. So on condensed formulas, you can use any of these noble gases, to write a condensed formula. So in a case where you know that neon is 10, so I know that if I count from here, it's 10. So I can just say sodium can also be written as using neon, and then I say 3s1. So this is a condensed formula. Let's look at another example. E, we have iron with 26. So this is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3p6, then 4s2, then 3d6. Yes, so this can also be written as a condensed formula. So we know that argon is 18. So we count from here 10, and all this represents argon. So I can do this and say 4s2, 3d6. So that is another way of representing iron using the condensed formula. Then on the same, you're going to find exceptions. So we have exceptions, that is copper and chromium. So for copper, the actual configuration, or the expected configuration for copper, that is a condensed formula, is supposed to be 4s2, then 3d9, but the actual configuration is 4s1, then 3d10. So it happens that this one is more stable as a configuration compared to the other one. Yeah, so that's it about how to write the SPDF electronic configuration. See you in the next video. Thanks for watching.